let's talk about the myth of single value. And I'm going to turn on a timer here, so I hope we don't use too much of everyone's time. This talk is about a pervasive myth that my students and I identified over doing some work this past summer. And what I'm going to try to convince you is that we should be teaching engineers how to target variability. And I will tell you what exactly I mean by that here in a little bit. But before we go too much further, I'm going to fight with my clicker because it would not be a real research talk unless I were fighting with my clicker. No, what I really want to say is that this is very much collaborative work that I've done with my students. So some members of Team URL are here. They're going to wave their hands for you right now. Mira is also a Team URL alum. This is very much collaborative work. This is work that I did with my students over this past summer. I am the sole person presenting, but this is very much the product of all of us working together. Where I want to start in terms of this story is way back in the 1950s. So in the 1950s, the US Air Force had a very serious problem, and that is that they kept on losing planes. And this wasn't due to wartime activities. This was due to pilots losing control of their aircraft and crashing them into the ground. And at the height of this whole basically fiasco, as many as 17 aircraft were crashing per day. So the Air Force had a very serious problem, and they tried blaming everyone. They tried blaming the pilots for not being good enough pilots. They had just invented jet technology, and they thought, well, these are not prop driven. They're just complicated. They're more performant. These people are just not good enough pilots. Then they tried blaming the instructors. Well, these instructors are just not teaching well enough. And they went through a whole litany of different excuses. And so one person, Gilbert Daniels, had a thought, which is, maybe it's none of those things. Maybe it's actually the design of the interface, the design of the cockpit of these aircraft that is giving us so much trouble. And if we take a look at what these cockpits, what these control systems for aircraft actually look like, that's a plausible reason for why things are going wrong, because aircraft are complicated systems. There's a heck of a lot going on here in terms of operating this system effectively. And so it's a reasonable question to ask, does this system actually work for the people trying to fly these aircraft? So if we take a closer look at some of the details here, if, for instance, we have a pilot sitting in this seat, and they need to reach one of these switches up at the top of the control system, well, then the butt-to-hand measurement right here is going to be relevant for actually sizing that correctly. So there are various proportions and measurements about a human being that really ought to factor into effective design of a control system for an aircraft, especially a high-performance one. Now, let me see if I can get rid of some of these zoom features here, because we don't need any of that stuff. So the 1950s approach was the following. The Air Force literally designed for what they called the average man. And now the first thing to note here is that already we have some suspicion that there's probably something wrong with this approach. The possibility of female pilots was not considered in the 1950s. Let's dig into this idea a little bit further. What the Air Force did is they took measurements of thousands of different Air Force pilots. They took measurements on all of their butt to knuckle measurements here. They found a data set of all of these, and they took the mean of all those measurements. And they said, this is the butt to hands length of the average man. This is what we're going to design our aircraft for. It is going to seat the average man and the average man only. Now, what Gilbert Daniels did, this thing is really misbehaving. Wow. What Gilbert Daniels did is he asked the question, well, out of the data that they had available, 4,063 Air Force pilots, how many of them were actually average? And I actually like to get some guesses from folks. How many people do you think out of this 4,063 pilots were actually average? Let's see, is that 5? Okay, 5 over here. Seeing 0 over here. Any other guesses? Good question.
Like how precision?
Yeah, how precisely are they measuring? That's an excellent question. Now, we could probably, apply a measure theoretic approach here and talk about, something being exactly average. Gilbert Daniels actually used a very generous definition, which is the middle 30%. The middle 30% along 10 different measurements that were deemed necessary for exercising in cockpit. So given that information, how many people do you think out of this sample of 4,063 were average, according to that very generous definition? 30%. 30%? A dozen? It was precisely zero. It was exactly 0 pilots out of this whole sample that were averaged according to 10 different dimensions. We can make a whole bunch of arguments here about dimensionality. There's a lot of interesting mathematics we can talk about there. I've got a backup slide about it if you really want to talk about it. But this is a really important finding. The Air Force, in designing for the average man, had designed for precisely no one. Literally no one could fly these planes. So this is giving us a sense of the kind of myth that was active, that was present in the design of these aircraft, which is that, well, most people are close to average. And this turns out to be just a myth. No one is truly average, especially when we start considering that people vary along all these different dimensions. But there's another myth that's related, and it's actually much more general, which is that engineering equations demand single values. This is essentially the kind of thinking that the US Air Force was applying in their aircraft design program. The truth is what I'm going to talk about in this seminar. So, what is the myth of the single value? There's a pervasive myth in engineering that mathematical analysis requires single value inputs. There are other techniques beyond this, which I will not discuss in this talk. But this approach is a dangerous one that has led to catastrophic failure and a loss of life. So maybe we should be teaching our engineers to do something different. Maybe we should be teaching them how to target the consequences of variability. And that's exactly what my research is about. So let me give you an overview of what I'm going to talk about for the remainder of this. First, I'm going to give you an overview of the study that my students and I carried out over the summer. And I'm going to report out 2 of the major findings from this study. First, the neglected, acknowledged, targeted analysis framework. This is a way to describe what kind of analysis did engineers carry out when they encountered a data set. And then we're going to present a model for how engineers think about variability. Can we explain the way different engineers are making these decisions? And can we use that information back within a teaching context to do better, to teach our engineers how to target variability? So, overview of the study. We carried out a human subject study over this past summer. We interviewed 24 different participants, and they varied along various axes. Here are just some summaries about the sample that we ended up reaching. So we had about a quarter of our participants were females. First of all of these people are practicing engineers. They're people with at least 2 years of industry experience. So not students, people who have been working in industry for at least some amount of time. So about a quarter of our participants were female. We had a pretty good diversity when it comes to race, at least relative to the fraction of degrees given out in 2020. We were looking for variability as well in the level of experience that our participants had, say ranging from folks who have 5 years of experience to folks who have just 2. And we were also looking at participants from different disciplines. So we were particularly interested in folks from aerospace, civil, and mechanical engineering. We ended up with one very interesting participant who currently works in the finance sector. You can ask me more about how that person ended up in our study a little bit later. So we interviewed all of these people, and here's a sample of the kind of questions we asked them in our interview. So we gave them a data set. We presented them with measurements on material properties. We asked them things like, well, these are the measured elasticity values for a cast aluminum alloy. How would you use the data to describe this alloy? And then we listened to what they had to say. Wow, this thing, God, okay. So that was just one question, but what we did within this interview protocol is we varied the type of question that we were asking. So for instance, this first one, we just asked them to describe the material that they're looking at. We gave them the material property of elasticity, and we did not provide any additional information, say an equation, to reason about how this affects some kind of outcome. And then we changed things, say asked another question about, well, here are some data on strength. And change things again. Well, we were talking about just describing before, but now let's talk about actually designing something, say design a load-bearing component using this data. And by varying all of these different problem features, essentially what we're doing is we're presenting different contextual features. So Mira, Ria, and I actually carried out a pilot study 2 summers ago, where we gathered some of the initial hypotheses about what might actually matter in this kind of a study. So actually, Mira, some of the work that we did 2 summers ago very much fed into the design of this whole.
Again, we wrote it, but the question here just showed
exactly what we did. That's because we were prototyping those ideas. So, given that background on what kind of study we carried out, what did we actually find from all of this? Well, one of the things we found is that, as far as I can tell, we've identified what is a previously unrecognized cognitive resource. And by that, I mean the way to describe a beneficial action that some engineers will carry out when they're analyzing data, and that some engineers will not. And that actually people will sort of deploy contextually and in response to different kinds of features within a problem. So this brings us to this idea of the neglected, acknowledged, targeted analysis framework. And so this is a way to describe what kind of analysis did engineers do. We put a data set in front of them. They made all kinds of choices. They told us all kinds of crazy stuff. How do we actually sort it into different buckets to try to make sense of this? So when an engineer carries out an analysis of data, let me get rid of this because that's blocking part of the slide here. Their analysis can either be neglected, acknowledged, or targeted. Neglected would be they're neglecting variability entirely. If we just take the mean of a data set and don't do anything further, that is neglecting the fact that there's variability within, say, this sample. Now, acknowledged is an intermediate point that's kind of interesting, where, say, if someone takes the mean and standard deviation, their analysis is at least acknowledging the fact that there's variability. They're explicitly acknowledging it in the mathematical choices they make, but they're not all the way to targeting yet. Where here, a person is choosing their statistical choices in order to respond to the consequences of that variability. That's a little bit abstract, so I want to give you some examples of each of these different rungs. Come on. So here's one example. Participant 1 actually took the mean only throughout the entire interview protocol. At no point did he do anything to just take the mean of the data set. And so here, in response to one of the questions, we asked him, well, how would you use this data? He said, well, I'll just go with assumptions first, and after that, I'll take the mean of these 10 samples. And based on the values I have, I'll look into, say, other resources. I'll compare my mean value against other published values. This would be neglected because his analysis is in no way acknowledging the fact that there's variability in the data. Participant 3 used a different approach. When we asked her, well, how would you use the data to describe this outlet? She told us, well, there's variability in the outlet, and I would probably try to find the mean and how much it varied over the sample of 10. Now, she's not specifying I would take the standard deviation, the interpolation range, what have you, but at least she is saying in some informal way, I'm going to try to quantify how variable these data are. Now, same participant with different question, we asked her, well, now what if you use this data for design purposes? In this case, she said, well, now that we're doing design, since for a load-bearing design, I want to make sure that I designed it well below at least one standard deviation of that tensile yield strength to make sure that it never deforms to the point where it won't return to its original value. So here, this person is actually taking some of those statistics she computed before, say mean and standard deviation, and is actually combining them to produce a value that's more safe for design purposes. And this actually starts to look a little bit like something that's a codified part of aerospace practice, where it would actually be illegal to design an aircraft using the mean tensile strength of materials. It would actually be out of compliance. You could not certify an aircraft that was designed according to that criterion. You actually have to use something called a basis value instead, which deliberately accounts for variability in material properties. And it's precisely because this is a potentially dangerous situation that variability has potentially real and devastating consequences. So what was the targeted approach that they used back in the 1950s? Well, if designing for the average man is not okay, here's a different approach. What they did is they took that sample of all of these different pilots. They have now some distribution of measurements, and they can select upper and lower bounds that respond to the variation they're going to see among their actual pilots. So here, they now have design criteria of this seat needs to be adjustable such that it can fit a person who has a vertical reach as low as 30 inches or as high as, say, 37. This is an approach using the data that is responding to the consequences of that variability, namely that it's real and we need to deal with it. This is an eye chart. I put this up here just to emphasize the fact that we interviewed 24 different people. We looked at their behaviors on all of these different interview tasks. My students tell me that this slide is incomprehensible. So we're not going to talk about this. We're going to talk about this instead, which is a simple comparison between participant 6 and participant 1. So participant 6 throughout the entire interview protocol used the neglected approach. He took the mean of the data set every single time, even when we asked him, you're going to design a load-bearing component that is going to be subjected to tensile yield, to a tensile load. You've got this data, how are you going to use it to design your structure? And he still took the mean. Now, this is in contrast with participant 6, who even at the beginning, when we said, how would you just describe this data? He started using targeted approaches and continued to do so throughout the entire protocol. So the question I have here is, why? Why such different behaviors from these two different engineers? And also, how can we train our engineers to be more like participant 6? What are the things that are important to nudge an engineer in the direction where they actually consider and respond to the consequences of variability? This is where we come to a model for how engineers made decisions, at least within this study. So what I'm presenting, we're calling the context-engaged engineering data analysis model. That's a mouthful. What I really want to talk about is a picture that explains the kinds of patterns of responses that we saw. So David Moore, a prominent figure in the stats education community, tells us that data are not just numbers, they're numbers with context. And so what we have here are really the core pieces of what data really are. We have both the numbers that we're trying to make sense of, but also the context in which they sit. We already talked about statistical choices, at least through the lens of this framework, that the choices an engineer could make might be neglected, acknowledged, or targeted. What we're trying to figure out is how are they actually navigating these choices? So there are two primary categories of the kinds of ways engineers are responding, at least from what we saw in our study. Things that we're going to group into what we're going to call engineering knowledge, things like, do you understand the fundamentals of, say, stress? Do you understand that stress is related to strength, and sort of crossing the threshold in one direction versus another is the relevant way to analyze this kind of problem? But we also saw things like psychosocial interaction. This is just a kind of messy way of describing both psychological factors, say the internal thought processes an engineer is going through, as well as social factors, say the social pressures that are being placed on them from, say, the organization they work in, also play a role in making these choices. I'm not going to talk so much about the psychosocial stuff over here. I think it's important, but just in the interest of time, we're going to focus more on, say, engineering knowledge and this idea of context. Now, there are some other attributes of problems that ended up being important. Things like consideration of safety and consequences. This has both the engineering knowledge and a social component. Say, I don't want to kill people with the designs I make. That's a social consideration, as well as these are the technical things I'm going to do in order to make a safe structure. That's an engineering knowledge consideration. But right here at the middle of this whole framework is this idea of a single value. This is something that we found to be very core to the way our participants were reasoning through these problems. So this brings us back to this myth of the single value. And there's an important distinction to make here. Is I feel like I won't editorialize. I'll just say there's an important distinction to make here. The first is a reality that when it comes to actually doing engineering, engineering design really requires single values. For instance, we need to have nominal values to put on a part design to hand over to a machine shop so they can actually make a part. That's just the reality of how engineering is done. But where the myth comes in is that engineering analysis requires single valued input. We don't have to do that. We have other techniques such as Monte Carlo analysis, something Brad talks about in circuit design courses, something that I imagine David Schumann talks about in probability modeling, something that I talk about in data science and PDO when I teach it. But this myth leads to these ideas like we're going to plug the tensile yield strength into this equation in order to carry out, say, the structural sizing. And these should hopefully give us some pause because, as we've seen, there's no the height of a human. Similarly, there's no the tensile yield strength of aluminum anytime we make it, even according to the same specification. So what we're going to do is we're going to use this picture, this framework or model, to try to understand how these engineers made these various decisions. So for instance, participant 1, the person who took the mean throughout the entire protocol, we asked them, well, why would you compute the average? And the reason he gave us is that, well, these values are pretty close to each other. So I feel like we should just take the average. The thing I want to note here is that none of these other factors are really sort of activating for him. There are none of these other considerations that are coming to mind suggesting, well, maybe I should do something different. And so there's this default approach that he's falling into, and so we end up with a neglected analysis. Now, even for participant 6,
God, I'm having to shuffle this thing all the way around the screen. Let's see if we can get rid of you permanently.
so participant 6, who is using a targeted approach throughout the entire interview, even he said, well, usually to use a property and say some sort of modeling effort or do a typical calculation, you obviously want to have one value that you plug in. So with a range of values, I would probably calculate the mean and use that. So that probably sounds kind of funny coming from participant 6, who it claims earlier was using a targeted approach. Because what we're seeing here
Is that
he's referring explicitly to this myth of the single value. It is something that he as well buys into, that there really is just one number that we should plug into the equation. And that number, more often than not, will end up being the mean. So it seems like both of these people are inclined to take the mean when they do data analysis. So what actually happens when someone doesn't do that? Well, we talked about this a little bit with participant 3, for instance, who we asked her, well, how would you describe this data set or this alloy? And she talked about finding both the mean and how much it varied. So her statistical choices are actually acknowledging the variability. She's not really responding to any context yet, but at least she's taking some different statistics and she has sort of the raw ingredients for doing a more targeted analysis. At this point, it's merely acknowledged. But what we can see is when we introduce the idea of, say, if we're doing load-bearing design, well, I'd want to design it to be well below at least one standard deviation of that tensile yield strength. So here we see multiple factors are activating in her mind. First of all, she's responding to the context that we presented. We're doing design now. We're not just describing things in the abstract. And she's also deploying her engineering knowledge in order to choose a statistic that is relevant to this problem. So participant 6, we're still left with this question, how did he end up targeting things throughout the entire interview protocol? And so here, this is a very early question, a very early response that we got from him, where he said, well, what we have here are 10 different values. I would use the mean value, but of course, you could always argue that you should use the minimum because then it's less stiff, and that would possibly be a conservative estimate of the deflection, if we're talking about elasticity, that is. So here, we're seeing multiple different things activate. Come on, Clicker, work with me here, work with me. So we're seeing, again, this reflexive approach that the first thing he does is take the mean. The mean is the default, as far as we can tell, for most engineers, and I would actually say, based on prior research, the mean seems to be the default for all humans, just the number we tend to reflexively compute. But for him, he actually introduced his own context to this problem. So this is just, we were just asking for a description, say, what would you do with this data set? But this participant 6, he's got a lot more industry experience. He's actually done a PhD. And so he's just sort of toying with different possibilities for how he might actually use this data. And so he actually told us, well, if I wanted to talk about, say, conservative deflection, I would need to choose something different and use a different statistic. So here, we were not even talking about deflection in this case, but he's just bringing into consideration, there are different applications I could think about, there are different uses, different ways elasticity might actually show up. And so for him, we didn't even present any context, he just constructed his own. So coming back to the comparison between participant 1 and participant 6, what we're seeing is that participant 6, using his backgrounds, using some of his disciplinary knowledge, is actually navigating context, in some cases actually deciding to invent his own context for how he would use the data. And that's what actually allowed him to target consequences in a lot of these different cases. Participant 1, fun fact, he built himself to us as a mechanical engineer, but the kind of mechanics he actually works on is printed circuit boards. So a lot of the questions we were asking, things like if we're talking about mechanical failure of, say, some sort of component under stress. Honestly, I had to reteach him some things about compression and like buckling failure. He actually had a reversed understanding of how elasticity affects buckling strength. And so in his case, a lot of the kinds of contextual features that might suggest a different approach were just not present for him. I would be really interested if we were to come back along, design a new protocol, talk to him about circuit manufacturing. It might be a different situation, but at least in the protocol that we had, it was me all the way. So what are the implications of this kind of work? Well, the thing that I draw from this is that what I really think needs to happen when it comes to improving stats education for engineers is to start to focus on this idea of targeting the consequences of variability. I think that might be the right slide. So what we've seen is that this myth of the single value, it has already led to catastrophic failures. And so hopefully I shouldn't have to work too much harder to convince folks that educators should really be training engineers to think about these kinds of things when it comes to variability. Because when it matters a lot. So what we've talked about in terms of this framework is that this idea of a single value is a myth to be overcome. This is something that we see very often within the stats education literature. There are tons and tons of papers that talk about this idea of, say, statistics education being flawed, that it's something desperately need repair. But this idea of actually targeting is something that I've not seen mentioned within that literature. What we saw is that some of these contextual features actually help to promote targeting consequences, say, highlighting these kinds of things for engineering students, the safety and consequences that are relevant when it comes to variability. That's something that could help. But I think in particular, teaching ideas like actually targeting variability using some deliberate statistical choices, say, instead of taking the mean, maybe we take an upper quantile or lower quantile. Or hell, if we want to get really fancy, maybe we do a one-sided tolerance interval. Now, I want to contrast this a little bit with the focus that is usually made within statistics education courses. So if we have some kind of a data set, usually the focus is on inference. Say we have a data set in front of us, there are multiple possible populations that could have given rise to this data. Usually the work that we're doing is we're trying to index all those possibilities and basically account for the possible states of the world given the data that we've seen. And usually within this whole kind of framework, we're talking only about the mean. We're talking, say, about putting a confidence interval on it. What I'm talking about is something that is distinct, but also plays well with this idea of inference. So rather than talking immediately about doing inference, I'm talking about, say, taking a data set and just summarizing it to what is a relevant summary that we could use for engineering purposes. Say, if we're talking about applied loads, what would be conservative is to behave as though the load is larger than it typically is. So let's just say take the 99% value of the loads that we've observed. And then once we're sort of moving in the right direction, there's some fine tuning we can make to say, do inference on that chosen statistic. But both of these ideas really need to play well together in order to bring some of these inferential ideas into engineering practice in a productive way. I'm on a clicker. We're almost there. This is what we saw the US Air Force do in order to solve their plane crashing problem. They had as many as 17 pilots crashing per day. The very simple thing they did is they went back to their data. They took upper and lower values coming out of that sample, and they used that as the design criteria coming back to their suppliers. They actually did something even more dramatic. They went to their suppliers and they banned the average. They actually said, we will not buy from you aircraft that are designed only for the average man. You have to satisfy, your planes have to work for all of these different ranges of possible values. And that's because what they found is that nobody was average, and they really had to address that variability directly using some kind of a targeted approach. So closing thoughts, this myth of the single value is really a barrier to safe engineering practice. And so what I think we need to be doing, at least to fix some stats education components when it comes to teaching engineers, is that we should be teaching engineering students how to target variability. That's all I've got. And I think we have a little bit of time for questions.
How did you think about like the way in which, you know, courses in which you're kind of like learning how to do these kinds of calculations in the first place? like, how do you target variability early and often in those kinds of courses where if you're learning how to, calculate the, where a beam might buckle, like you might be kind of teaching that you program just learning it.
Yeah.
How do you kind of incorporate that?
That's an excellent question. Like, if we get down to the nuts and bolts of it, how do we actually do this? And it probably shouldn't be, let's throw a whole bunch of additional statistical ideas in. Probably needs to be something a little bit less thought. So this is the kind of work that I'm doing next, which is getting into the details of now, how do you actually, like, nuts and bolts teach these kinds of ideas? But I have some hypotheses as to what might actually work. So one thing that we know in mechanical engineering is that our students and engineers tend to be very good about recognizing the fact that there's variability in geometry. Like, I don't know if you've ever worked in a shop and you've had this scare thing yet where you say, well, if you hand a drawing over to a machinist that doesn't have any tolerances, what they're going to do is they're going to go and they're going to manufacture the thing to optical tolerances, and they're going to charge you an arm and a leg. And I think that's partly because of the representation, where the way we talk about geometry is often in terms of a nominal plus and minus tolerances. So even in the language you're using to describe those things, we're acknowledging variability. And that at least gives someone the awareness to start to think about why that might matter. When it comes to material properties, it's the complete opposite. Where if you go to your phone right now and you Google, say, tensile strength of aluminum 6061, you're going to get just one number. And so it's built into the way we even report these values, the way we even encourage our students to think about them, the way we trade information across organizations is just in terms of single values. So something like, say, this nominal strength plus or minus this basically error, it's not getting all the way to fixing all the problems, but at least it's suggesting that something else is going on here. And maybe I should at least acknowledge that variability. It kind of seeds the ground for doing things later. When it comes to, say, getting students to the point where they reflexively target variability, analyzing a data set, I don't yet know how to do that, but it's something I'm working on.
So on the timeline from like prototype to polished design, at what point at what point in like an ideal world in education would students start incorporating variability? Because I know when I'm prototyping, it's kind of like I need to get something that works under a condition. And then it fails later.
Yeah, great question. So one related thing that I'm going to peel back in the study is that because we were studying both mechanical engineers and civil engineers, we got to see some really interesting features when it comes to the norms and realities of how engineering is done. So for instance, for mechanical engineering, honestly, you can probably go prototype something just using nominal values. You're going to go break the thing. You're going to see what happens, figure out what are some of the mechanical things that have gone wrong. And then you're going to continue to scale that up towards production and start making, say, larger and larger batches of the thing and discover new and newer problems. Within that whole context, honestly, you could get away with using the mean the whole time. And part of that's because you're doing the experimentation that's necessary to prove out this thing actually works at scale. Now, you could do it more efficiently if you were actually thinking statistically earlier in the process. But that's very much in contrast to civil engineering, where you don't get to build 100 test buildings. You have to build one building that is guaranteed to work and not kill people. So we actually had one participant say to us very strikingly, there are no prototypes in civil engineering. You have to get this right the first time. And something, if you look at the actual textbooks that civil engineers use for the training, variability is front and center within even the introductory textbooks that they give to students. It's very much built into the way that they think about these sorts of things. And so the safety factors that they're using, I'm just kind of in awe of civil engineers, like to be honest here. Like the more I've learned about how civil engineering practice works, I'm just so impressed at how rigorous they are about treating sources of uncertainty. Even their safety factors are rigorously calibrated against probabilistic models. They're not just made up numbers like in aerospace. Some of them are just made up numbers. Some of them are rigorous, but like the 1.5 safety factor in aerospace engineering, it has no rational basis. But in civil engineering, it's been very carefully constructed. So to answer your question directly, kind of depends on the discipline. Civil engineers already get a lot of training thinking about these ideas. Mechanical engineering, it may not matter unless someone actually goes and they start to specialize in, say, industrial engineering. we're there, you really need to think about how we get this to scale. How do we actually grapple with some of those consequences of variability? But at least when it comes to the very basic idea of variability exists, what we can see is for participant one, he's not even necessarily recognizing that fact, at least as expressed by the analysis choices that he's making. And so I would like to at least prod a little bit in the direction of getting more engineers to recognize that variability exists. And hopefully try to. Okay.
Right. And then you skip on the slides that make you ask.
Sure. Should I hop to a different slide here?
Yeah, which is, I'm curious to know what the
Oh, man.
I know it's kind of scary.
Oh, we get to come to the eye chart. Yeah.
Yeah, what happened here?
Right, so just in your reflection,
Huh?
how you see most people want.
I think what I'm hearing here is, did I see people who would target variability most of the time versus people who wouldn't? And I will admit that was kind of my expectation coming into this. I would say that expectation was actually quite wrong and quite. This was a really eye-opening study for me to carry out because there's a lot more blue in this chart than I was honestly expecting. And I was really pleasantly surprised to see that because based on it, like if you read the stats education literature and look at studies of like how people make decisions under uncertainty, often it paints a very dismal picture of like nobody understands probability. Everyone's making foolish choices all the time. But when we take a look at, say, some of the particular behaviors that engineers are making, a lot of them are actually choosing things like, let's just take the minimum of all these numbers. That's not a terribly statistically, like inferentially sound thing to do, but in terms of targeting consequences, that's the right direction. And so this is in some ways it's a particular lens. It's hiding other things, like especially the inferential parts of doing data analysis. But it's at least representing things like, is a person responding to the consequences of variability? I think one thing that jumps out to me about this is if we take a look at this middle bunch right here, we see a lot more blue. And that's because that's where we're actually talking about design. And so something that was encouraging for me is that a lot of these engineers, when we actually put a design problem in front of them, they say, okay, this is serious. I need to take some kind of principled approach to summarizing these data. By and large, they actually did a really good job targeting those consequences.
So if we presented the data to somebody and they said that they would just design for the minimum values and that their part would be able, they would like, would be able to withstand that type of load, would that could be considered as a little bit?
Yep. Well, so it depends on the context. If we're talking about strength data, taking the minimum value, yeah, because what they're doing is they're responding to the potential outcome where I make a part, it ends up having a lower strength than what we typically see. If I designed in my, say, original sizing for the mean value, then I would not have enough capacity to withstand that load. And
Did you also describe why there is this is as what you were
oh yeah, so yeah, the other. So this guy did an engineering undergraduate degree, but ultimately went and started working in a bank. So he switched fields. He's still using some of his quantitative skills, but in a very different area. And so honestly, he didn't remember a lot of the nitty-gritty details of like how do say columns work when it comes to buffering, that sort of thing. Actually, yes. So here, for instance, when it comes to the column design problem, he didn't choose a targeted approach. One thing that was kind of surprising here is even for this person who is pretty rusty when it comes to engineering knowledge, would still target the consequences in some cases if, say, we were broad hard enough. Something like strength. Actually, one of our participants said this pretty directly. A material property like strength basically never gets used unless we're talking about failure. And so it already has this very strong connotation built in that we're talking about something that's very high consequence. Whereas something like, say, the Poisson ratio of a material, what does that do for us in terms of failure? There are probably not many engineering failures that have hinged on an incorrectly measured Poisson ratio because it's almost always stuck around 1/3. So what we're seeing is that these contextual factors, even for someone who's kind of rusty, they can potentially nudge them in the right direction. No?
So earlier, you were kind of talking about designing with this idea of the targeting approach in mind. And so what I've always been taught is that you design with a safety factor, the very reason of this variability. So my question for you is like, if you take into account the variability directly and assume a target approach, do you think it's appropriate to then lower your safety value? And
Yeah.
or like, how is that? Like, do you prefer one over the other, which one's better, which one's more convenient?
Man, this is the point where we have to say it depends. And it's a very big, it depends, because safety factors mean very different things across disciplines. Where, as I mentioned earlier, the safety factors in civil engineering have been very rigorously calibrated against a whole bunch of things. So they consider things like material variability. They also consider things like, they've actually gone out to job sites and looked at different construction companies, different operators, and they've seen how much variability is there in the concrete strength based on how it was actually poured. Like, this is the manufacturer variability that they actually enter into ultimately how they calibrate those safety factors. Something that's so smart about the way civil engineers did it is they did all of that work to arrive at these safety factors, and then they actually, at least in the US, for things like, and this is where I'm not actually a civil engineer, and I get things confused because in Canada and in the US, they actually have very different approaches. Well, even in the United States, they actually use the main strength. But then what they have are safety factors that are calibrated to account for all that variability, so that for an engineer just doing design shop calculations, they can get away with using all those mean values. But it's because someone else has done all the work necessary to say, if you put the mean value in here, I've accounted for that within the way we've calibrated all the safety factors. We can talk later about allowable stress design versus load and resistance factor design, which is a reformulation that actually allowed the civil engineers to get greater performance gains when it comes to a more comprehensive treatment of uncertainty. That's something I'm going to punt outside of this conversation, though. Basically, if you do more work, you can operate closer to the margins. You can have more efficient structures. That's the short version of that story. Bill, I think you had a question too.
Yeah, so you've mentioned that, participant one, right, PCB manufacturer is 2%, they're not, they're special needs, they're low less key. And as we can see, they're like one of maybe like two or three people who actually have maybe like a sprinkling of kind of neglecting choices. Do you think that, or I guess like, do you see this project moving forward, kind of studies like this and work stuff at work? And if so, like what kind of further directions do you see?
Oh, that's a great question. One is just taking this idea of targeting variability and trying to get it out there. So like, this is work that we've submitted for journal publication. I'm hoping to get this idea in front of more engineering educators. And we have projects right now, Katie, Emma, AJ, we have projects right now basically trying to extend these ideas to do things like ask questions like what sources of uncertainty are even recognized as existing in different disciplines. Emma's working on a project right now where she's trying to understand when we say error within engineering, like what do you actually mean by that? Like what do you mean by error? Because one of the questions we asked him here was related to error, and we saw a hell of a lot of different ideas about what people think error is. So this I think is sort of the foundation that I'm going to build a lot of our other ideas on top of.
So frequentist and business
Oh my
specific.
God, no.
All right,
No, we're not doing this.
all right,
It works for either. That's
okay,
my answer.
fine. Gonna keep showing up and asking you that question in different cases.
I think we have time for maybe one more question.
It's a dumb quick question. What are the green squares?
These gray ones?
Yeah.
This
Oh, that's
is-
correct.
This is frustrating. This is where our video got corrupted. So we recorded all of these interviews
Nice one.
and Zoom failed us. So the beginning of this interview was just unputable. It's not exciting. It's just, yeah, data errors. It's error.
Error.
Error in the
What
line.
do you mean by that?
All right, folks, thank you all for coming. I'll stick around if there are any questions.
Thank you.
Welcome.
Well, I actually had a question.
Yeah.
Wait,
Give
yeah,
it to me,
so
man.
it's just like, oh,
It was on the slideshow.
Okay,
So, let's see.